I hope you enjoyed lunch. Please feel free to bring food in here if you'd like, if you're still nibbling. All right, so we are going to pick up with our afternoon. I also want to just call out that for all of the sessions, please do know that you can rate the sessions as well as the overall program using the QR codes on the tables. So those are available to you at all time. So please give us your feedback on individual sessions as well as the overall program. We're going to start the afternoon with our next speaker. Dr. Belal Hasan is going to be talking about biotechnological processes application in developing functional properties of plant-based ingredients. He's going to explain what that means to me. So, with further ado, I know you all know Dr. Hasan. He's a faculty here in the Nutrition and Food Science Department, assistant professor, as well as great collaborator and friend of mine. So, I'm happy to introduce him. Welcome, Dr. Hasan.
Hello everyone, and good to see you again. So sorry about the long line for the lunch. Apologies. We learn by doing, so we learn by doing. And as you see, I'm wearing many hats today, so I'll switch hat from the chairperson to a speaker. And today we're going to talk about the biotechnological process application in developing functional properties of plant-based ingredients. And this project was established by me, Dr. Jing from San Diego State University, and Dr. Olive Lee, who is the person hired me in Cal Poly Pomona. We got funded from US Pulses, and you'll see at the end the project number and the details of the project. So the growth of plant-based in North America is about 6 billion in 2025, and is expected to grow up to 12%. In Europe, we expect about 10% growth, and in Asia Pacific, we expect about 15%. And in other countries, which is still a lot of resistance for plant-based diets, I think Middle East, some regions in Africa, the growth is way lower, and that's have something to do with the cultural. However, we see the expansion in Asia have led us to think about what type of diet that we should be thinking to develop that meet the culture needs. And with all due respect, I know we have so many experts here today. The plant-based industry was run by industry, mainly Western fast food diet that meet the demand for certain number of consumers, with ignoring opportunities with other cultures that they need products fits to their cooking. And for that reason, I established a project with a couple of my colleagues, Dr. Jolie Lee from agribusiness and Dr. Dennis from the communication. We thought of doing something called bottom-top rather than top-bottom. So usually the industry designs something and they say, oh, this is the best, it's a good product, tastes like meat, smells like meat, but it's not meat. However, we want everyone to support it, and with that adds up to the cost. We thought of starting from the cultures, asking communities, what do you want? Do you care? Why? What are the reasons you don't eat plant-based? And we found simple answers, like how I can make patties into tacos. Simple. Yeah, makes sense. And another response, 10 patties plant-based cost about close to $25, but 10 patties of Angus beef cost you about $7, $8. So if I have a family of 100 people I'm inviting for a dinner or something, I need about fortune. It's like $2,000, $3,000 just for the patties. So we developed such thing. Today I'm not going to talk about it in details, but it's just something that we're working on to develop a program that involve the consumers and building toward what our cultures and what our communities actually need. The current status of meat supplies, especially the plant-based proteins, including the meat and the milk, dairy products, we currently meet the demands, and that's a good thing. However, by 2030, we will have 10 to 20 million metric ton in shortage, and by 2040, that will increase to 30 million, and of course, going to be 40, 50 million. And just to share with you, 10 million metric tons of of animal proteins, you need about 30 million acres of land to produce it. Because earlier, Albert talked about the land. We're really limited on land, especially in California, it's too expensive. But Midwest, even Midwest, is really, we're limited on the land. We cannot have another 30 million acres dedicated to growing animals. The second thing, we need water. 1 kg of animal protein needs about 15,000 liters to produce. Do we have that much of water? And I think Albert again mentioned that growing crops, feed it to animals, eat the animals. Economically makes much more sense if we just consume the plant base. Grow them, eat them. Easy, cheaper. The current commercial plant-based protein depends on soy protein, isolate, concentrate, or texturized, which is 80% of the plant-based industry. We did a survey. We collected, my students, not me, collected about 500 products from the market, and they did this. We published it in one of the books in Elsevier. 80% of the products still use soy protein. Unfortunately, is allergies. The second is the wheat protein, which is gluten. I'm a new Californian, but we believe there's so much gluten in the world, so we want to cut on that, so many allergies. However, it's good elasticity. And elasticity, for those new to food science, is that chewing, that's satisfying chewing. That's elasticity. So when you chew on bread, it's totally different from bakeries, because bakeries have very low gluten. So that is satisfying. However, there's challenges with the allergies. Mycoproteins, I love them. Really good source of proteins, complete. The PT gas is high. We have essential amino acids. The problem is the scalability limitations. So we need to grow more and more of these fungus to build mycoproteins. And we have the pea protein isolate, which is about 50% now is using it, allergy friendly. But the big challenge is the poor flavors and the texture. Future, we're looking at lentils, chickpeas, and fava beans. And for those who are new to California, lentils can resist drought and high temperatures. There is a lot of farmers start to grow them in Fresno and some parts of that desert of California. The problem, they don't know what to do with it. I mean, I wish I was back in India. That's a lot of dal for us to cook. But it's new, so they don't know what to do with the lentils. We thought of, let's do something with the plant-based protein. In the future, we can work on all of these. So we're taking those in consideration as alternative proteins. So the pea protein limitation is the taste, earthy or beany flavor. That's a big issue. Bitterness, we need a lot of flavor masking, which is challenging because when you mask it, you need to spend money. It's just, I want to regrow my hair. If I do the transplant, it costs money. So think of that. You need to spend money to mask the flavors. Texture limitations, we have less elasticity, so it's not chewy, which all of us want to, help Mother Earth, but Mother Earth needs to give us something tasty, something we can chew on. Dry or crumble, mouthfeel, so those are the challenges, and poor gelling capacity. We also have nutritional issues, which is anti-nutrients, especially the phytases, because they prevent the absorption of proteins and absorption of other minerals like iron. So just for you, the native protein is usually something folded. We do process, we call it a denature. We have to process it some way with a pH, change of acidity or temperature. We want it to be open up, so we can do a lot of activities like gelling, foaming, so it's become functional. Think of your pudding or custard or any of these products. If it's native protein, you will never retain that texture. So we need to do some denaturation to have those activities, which is protein known for gelling, water holding capacity, foaming, and other things. So the current process called alkaline and acid precipitation, where we take the proteins, the pea proteins, solubilize them in alkaline, centrifugation to get the precipitate. We use some acids during the centrifugation, and we get the plant proteins precipitated by the acids. So it's a standard process. One of my colleagues here, Dr. Zari, he is expert in this process. That's what most of the industry using now, and I'm may be wrong. Albert is from Ingredient. They supply a lot of ingredients, so you can ask him. The problem is generating of waste. So legumes or seeds have only about 20 to 30% proteins, and the byproducts like starches, fats, fibers, what are we gonna do with it? Because we are interested in the protein. Most of us now, especially the younger generation, interested in the protein. Loss of nutrition quality, a lot of the high acidity temperatures may damage the amino acids and reduce digestibility. And I think that's the nutrition. My colleague from nutrition can tell you more about it. Environmental concerns, we generate a lot of waste, the pH, the minerals we use, and we have to find a way not to dispose it to the nature, so it can cause some environmental damages. The low yield, because the protein, a lot of proteins are insoluble, so we will not be able to solubilize it. It will be with the byproducts. And the cost, because we're doing all these processes, maybe 6, 7, up to 12 steps, we're adding cost to the proteins. So for today, we're talking about bioprocessing or fermentation. I like to call it bioprocessing, and it's just for one reason. I think in North America, when we say fermentation, the first response of the people, oh, kombucha. It's like, it's more than kombucha. That's why I like to use bioprocessing. It's just like, oh, it's a fancy name. It's a fermentation, but we call it bioprocessing just to add up, to get funded, honestly. So the technique is using microorganisms like bacteria, yeast, fungi. Is nothing new. We could use the enzymes for more controlled conditions, and we can create a desirable compounds under controlled conditions. The controlled conditions usually temperature, pH, inoculum size, the type of the media we use. So there are multiple factors we use. We do have enzymatic modifications, we do liquid fermentation, and we do have solid state processing, and that's what we use in our research today. The type of bioprocessing, as I mentioned, liquid state bioprocess, it is submerged in the liquid. It's common in beverages like kombucha, easy to control pH and aeration, higher water use, which cause a lot of downstream process. For me to recover the proteins, I need a lot of a process like centrifugation, drying, a lot of steps which add up to the cost. On the other hand, the solid state is low moisture, so I don't need to submerge the material. Common for protein-rich material like soy, lentils, is lower water use, energy efficient, because we don't need so much energy to dry it, and controlled products. It's difficult to control the pH, that's why we need to be very careful when we design processes. And this is just a mechanism showing you how SSP is expected to improve the functionality of pea protein. So we have the pea protein, we process it, we inoculate it, we denature the protein, we have improved functional properties from the denatured protein. The degradation caused by the enzymes from the microorganisms break down the anti-nutrients, especially the phytase, make it safer for you. And of course, the off flavors, all these beany, grassy flavors are actually embedded in the protein. So when you cause any denaturation, damage to the protein, you actually release most of these flavors. So these are the reasons to research about improved functional properties like gelling, emulsification, texturization, reduce the anti-nutrient agents, and environmental benefits, which is great papers out there, especially in the last few years. So from our previous research, we did some work on liquid state and solid state. We got the chance to play with orange pommes, watermelon, rinds, pineapples, almonds, rice, and we found that those are amazing. You see all these colors, so we extracted natural colors, natural flavors, but we also found that we can isolate proteins, especially from one of the example is the SPG, the BSG, the brew spent grain, which causes high in protein. So we found that if we do liquid state, we can isolate a lot of the functional compounds like flavors, like colors. And if we do the solid, we can convert it into material that can go as a part of the plant-based proteins or plant-based food. A patent is commercialized. This comes from a solid state, is now used as a natural fungicide for mangoes. One of my first PhD student, He's in Sri Lanka now, working on the mango project, and Sri Lanka produce about 13% of the world mangoes, so they needed this project. Another project we work on is a solid-state fermentation of glutinous rice, which has no taste, but with the yeast and with some other lactic acid bacteria, we generated some flavors like sweet to acidic. And we did a animal study, not a clinical study, and we found out like, oh, the mice love it. And we asked animal behavior scientists why the mice like the food we provide, not the actual food, their natural diet. And we learned that mice, rats, and monkeys have a natural instinct to find healthy foods, which is good to learn for me. And we ran some experiment on that. We did T cells, B cells, which saw some improvement in the immune system. So the fermentation, the bioprocessing is really important. It can help to improve the nutritional value of the ingredients. The BSG, that's something I love to work on. One of the projects we just completed. So BSG, why the BSG? A lot of production, especially in California. We produce almost about 15% of the nation BSG. It has about 75% water, 7% protein. We dry it with a simple process. We get to milling. We get about 32%, and with air classification, we produce about 65% protein, which is amazing. The only problem, the flavors, because you have the barley and you have other things. So what we did a solid-state fermentation to improve the flavors, and we extruded into plant-based meat analogs. Not much we can share with this. It's still in a process. It's an NDA with one of the clients we work in Southern California. For the current research, we get pea protein from the US pulses, recommended from suppliers who grow the peas on Montana. In Montana, we have a beanie flavors, which is hexanol. We have a poor functional properties. However, we run it through the fermentation with the hope that we improve the aroma compounds like aldehydes and ketones, and we boost the umami and glutamic acid. Don't ask me about chemistry. I have Jing Zhao. She's sitting at the back. She's my collaborator. She knows all of these details. I'm working on the functional properties, like the enzymatic hydrolysis, improve the gelling, the texturization, and improve the oil holding capacity, which is very important when you develop plant-based meats. So our research hypothesis was solid-state bioprocess will reduce beanie flavor and increase flavored volatile compounds. The second hypothesis was solid-state bioprocessing will improve functional properties of pea protein concentrate. And the last one is combining the bioprocessing with extrusion, we can generate a high-quality meat analogs. The independent variables we worked on is a prehydration, because we wanted to reach to a level, we prehydrated to grow the microorganisms, but not to exceed the use of water, so we can save on the energy. We don't want to use extra water that is not needed, that we will eventually need to dry it and add up to the process. The second thing is the time. We wanted to know the best time, so we decided to work between 6 to 24 hours. And 24 hours, we didn't want to extend that because we are afraid of food safety issues, maybe creating other challenges, and to make the process feasible, because you don't want to run it for 48 hours. It's a batch to batch. You need a very large facilities. So we wanted to make it shorter with more efficiency. The temperature between 30 to 37. And the dependent variables we were looking at is the pH of the fermented products, the flavors, the protein functionalities. We tested the solubility, water holding capacity, gelling, and many others. And the extrusion properties, checking how the texture profile will look like. So in the method, in the first stage, we got the microorganisms in a small sachet, which is only about 2 grams. We needed to grow them, create a stock culture, and we just mix 100 grams of pea protein with some water tap and 50 grams of glucose that help the microorganisms for energy source. And we grow them just for 18 hours. It was a two-in-one. First, we want to enlarge the size of the inoculum. Instead of 2 grams, we ended up having 2 liters at very high concentration. The second is adaptation stage. So microorganisms usually growing, lactic acid bacteria growing in milk, so we needed to grow them in the pea protein for them to adapt. And the beautiful thing about microorganisms, they have very adaptive proteolytic system. They've been on here on Earth for the last 10 million years, so they find their ways to degrade the food. And at the same time, we grow the size to 10 to the power 13, which is a good inoculum. We will need it in the prehydration. In the second stage, that's stock culture. We created a working culture out of it. So the stock culture was preserved at -40 for further analysis and process. But out of that, we started to make our working culture. So technically, the 2 grams, we converted to about close to 400 liters. For the solid state fermentation, we found that 40% is the best, and you will see it in the results in the next slide. And we did use the working culture as a prehydration for the pea protein. That's why it's so important to convert the 2 grams, the original sachet, into 400 liters, because we're going to use that working culture to hydrate the proteins and do the process in a shorter time. So if we just use water and dilute that culture, it's not going to deliver the same results. So we had to do these 2 steps to develop a feasible process. And when I say feasible, it's scalable. We could manage, I mean, we are limited on space and facility, but we pushed that to up to 100 kilograms, which is great. And we're progressing. And we're seeing the same results between 100 grams, 10 kilograms, and 100 kilograms. We saw the same trends. And again, overall process is a pea protein, fermented, extruded, and we're looking at all these parameters. We tested at 40, 50, 60% water content during the extrusion. And the goal is to build some meat analogs with a high quality and acceptable by the consumers. So the first thing, we observed that not all peas are same. That was a big challenge. And I think Albert again covered on the breedings is different. You grow them in different regions. You have different process to extract the pea protein. So that was the first challenge. Not all pea proteins or pea powders are same. So we needed to be very careful getting the knowledge how these pea proteins are actually processed. And therefore, we tested multiple samples, including sample A. We found, oh, this is not very suitable. We have some issues. But the good thing, the water activity was high, even at 30%. But as you see, even 30% is difficult to process because it's very wet. The second sample showed better results. I can say up to 40, 50. You don't see that liquidy behavior, but we still have the water activity above 0.9. And the third sample, which we work with, is sample C, showed a good water activity at around 40%. And for water activity, for microorganisms to grow well, like lactic acid bacteria, you need to keep it on more than 0.94. So that was the main thing. How much prehydration I need to use with the water activity that's suitable to support the microorganism growth, so we can see improvement in the functional and chemical properties. So we did measure the starter culture size, and we found out, yes, the working culture supporting the growth, the stock culture, the working culture, and all the fermentation hours, we reached 10 to the power 13 microorganism growth, which means the selection of the water activity was perfect. We have a growth, and that's a very good sign that the process is doing its job, or the microorganism doing their job. That was very interesting, and I had a very good conversation with Gabi and some other scientists from the almond board about the challenge with the powders. A lot of the powders in the food industry, they have a particle size less than 100 micrometers. And below 100 micron in the process, and like extrusion, which my colleagues covered, is really difficult. So we needed to do something called agglomeration to increase the size. However, we noticed by the fermentation and introduction of water, we already have agglomerated powders. And even when we dry them, they maintain that average size. So we have something improved in flowability in the process. And that's very important from point of view of a process. And even with extending the time of the fermentation up to 24 hours, the distribution was bigger, but the size was always above 100. And that's just perfect. You want something between 100 to 200 microns to fit for extrusion process. The second finding, we saw the pH. We don't want to drop the pH below 5.6 because from our previous paper, me and Jobing in 2023, we found that the pH below 5 is not that good for texturization. The protein seems to be aggregated, and you will have something hard in texture and not chewable. And we want something elastic, not a fragile. So that was a good thing because we confirmed even in 24 hours, the pH didn't drop below 5. The protein solubility was reduced, and a good reason for it. When we hydrolyze the protein, we exposure the hydrophobic amino acids, which in pea has 20%. It's very high in pea protein. Very, very high. Because casein have like 15, 14%, so it's really high in hydrophobic. So when we hydrolyze the protein, breaks down, we expose the hydrophobic amino acids. The second thing, the protein aggregation caused by the pH. When you have a pH, protein seems to collapse and aggregate, so you lose the solubility. We saw the water activity, holding activity reduced tiny bit, and is expected because we break down the proteins into smaller size, but the oil holding capacity significantly increased. And just a question, where do you get your flavors in the food? Is it from the fat or from the water? I mean, the liquid phase or the fat phase? Yes, because if you try to drink skim milk and the whole milk, you will immediately know the difference. And something like Wagyu, beef or Kobe, actually we're paying for the fat, it's not, it's the marbling. The flavors, 85% of the flavors in the fat. So that's a good powder that hold more fat. And I'll just show you, this is what happened, according to AI. So for a protein, you have a large size of protein, you improve the water holding capacity, because just think of a protein become like a balloon, hold the water. However, when you break down the protein into smaller amino acids and expose the hydrophobic amino acids, hydrophobic means they hate water, so they are good friend with fat. So the powder can retain more fat and retain more flavors. The gel strength was significantly improved. And again, pea protein is very poor. That's control in their gelling capacity. So after the fermentation for 18 to 24 hours, we see a significant improvement in the gelling. And the main reason, as you see here, even though the gel with a good water holding capacity and the size is big, but it's so soft. It does not resist the compression. And eating food is about compression. You bite on the food. However, in the fermented one, because of the pH and the aggregation, we form a gel that's more aggregated and is less size because you have less water in it, but it's much harder. And not only harder, we tested with some of amazing tools that we have called rheometer, and we found it's highly elastic, so it resists the fracturability. So when you bite on it, it resists. You can chew on it at least 10, 12 times before it breaks down. And this is what actually happening. This is the original pea protein, according to AI. And this is what aggregation looks like. So you have more particles or molecules sticking together, less water, less in size, but more elastic. This is the extruded sample. This is what we got from our small extruder. Again, thank you. We appreciate Thermo Fisher being partners with us. helping us to figure out the best conditions, and we optimized everything in details. Not only optimized, but scalable. So now we can produce it in our 11 millimeters that we have, and we can take this into 30 millimeter, and we can take it to 150 millimeter, which is the largest extruder site. Those are some of the samples. We found out that 40% during extrusion is so tough. It's like eating a low quality meat. We avoided that. We focused on 50 and 60%, which gave us really good elasticity, good flavors, good texture. That's the hardness. As you see in the control is really hard, but hard does not mean elastic. So we just wanted to show here, compared to carrots and meat, which one is harder? Carrots. However, when you take a bite of carrots, what happened to the carrots? What happened to the meat after first bite? Literally nothing. So you are not interested, and that was a big misconception among a lot of researchers and product developers. Oh, it has to be hardness. Yeah, but you are mimicking meat, which is not hard. It's elastic, it's chewy. So we showed here, it's not about the hardness. Yes, you have something hard, but you take a bite and fractured. Compared to the fermented sample, which is not as hard as the control. However, you can chew on it because internally there is a strong cohesiveness. And this is what's happening in the extrusion. We thought of sharing with you. The aggregated plant protein, when it goes to the extruder, they actually realign because of the shear and the kneading and cross-linked. So regardless our process, those aggregated protein in the extruder, which is an amazing device, you will realign them, you will cross-link them, and you will generate a fiber-like. So not to worry about the aggregation, because it was a big concern when we do the bioprocessing, the aggregation may affect the texturization. And we found out, no, actually, it's improved the texturization. We check the water holding capacity of the extruded meat analogs, because we want to check if our theory is correct, that the aggregated protein actually realigned and cross-linked. And we found there's no differences between controlled 6 hours up to 24 hours fermentation. The water holding capacity, which is a good indicator, simple, easy to do, we found out there's not much changes, which means, yes, the extrusion actually bring those aggregated proteins, align them, create fibers. However, it's going to be more elastic, less hard, which is meeting more qualities of a meat rather than just something hard, fracture in one bite. We checked the phytic acid, and we saw some reduction, not significant, but we see some good reduction, and that's a good sign. And the main reason, another student working on almond protein, we're doing the same process for almond, mixed with lentils protein, fermented lentil proteins, because lentil contain iron, and the biggest enemy of iron is phytic acid. So we are developing an energy bar combining the lentils, almonds, dates. I'm not supposed to say all the ingredients. The student looking at me from the back there, but we should be fine. We all patent it. So we found out when we reduce the phytic acid, and the next slide, the tannins, the absorption of the iron increased in clinical studies. We haven't done the clinical study, but we saw some evidence. The next slide. We did the tannins. That was significantly reduced. So as you see in the control, we had about 10 milligrams. We have now 4 milligrams. We didn't have the time to do all the analysis. They just finished it last week, but we thought to share it with you. I'm not the expert in flavors, and that's why I insisted Jing and her gang, group of students, yes, to join us, because she's the expert in chemical analysis and the chemistry part of it. I never got more than C in chemistry. But I learned something, that between control, extruded, and fermented, we saw some significant changes. And the significant one is the hexanyl, and the hexanyl 3-methyl was totally diminished. And those are the main flavors, grassy, beany flavors. They're still working on it. How to pronounce this? Heptonin was disappeared, and we saw some other changes, significant changes in the flavor profile. Again, it's not easy to do the work. They do have amazing facility down in San Diego State University. They do ENOS, they do the GCMS analysis, and we're working side by side. Future work, sensory evaluation is something we're looking at because we don't know if that meets the consumers, and back link it to my colleagues, Julie and Dennis. We work on consumers' needs. So we want to bring this and do the sensory evaluation and see if that really meets the consumer's demand. Because we have heard some really different feedbacks about the pea protein. Second thing is the nutritional profile, especially the PDCAS. I think we started on that, and I can share like out of 10 proteins we bioprocessed, including almond, including pea and lentils, the PDCAS always increased significantly. Large-scale fermentation, that's something we want to jump up to maybe 1,000 pounds, 2,000 pounds once we have a facility. The good thing is US Pulses and USDA is supporting those projects. And the last one is the downstreaming. As we mentioned, we need to have some water for the bioprocess. So we need to dry it to produce something called the super pea powders. Sounds cool. Super pea powders, and super by super means flavors, texture, texturization, and some other functional properties. And I think I have very last slide. Sorry about the bees. I don't have individual pictures with my colleagues. Jing Zhao from San Diego State University and Olive Lee. You met her in the morning. I think we brought close to 400,000 or 500,000 in the last 2 years. Every time I have them on a grant, we get it funded. And I have my students, Shirley and Elizabeth, behind the scene. They did most of the work, all the work, actually. And I have Jerry Lauren, who's also a master's student graduating soon. He helped them a lot. And I have many other students working in the lab, and we building that new belief. Let's do something clean label, meet the consumer's demand, keep it at low cost, so we have everybody a winner end of the day. Thanks to USDA and US Pulses for the project funded, and we're looking forward to continue this work, and I'm open for any questions. Thank you.
Thank you for the great presentation. And do you think all these processes affect the phosphorus or potassium content of the peas too? Or do you have any idea of?
We don't know in the details yet. However, we just learned from University of Minnesota, they offer us something very kind, which a full mineral analysis, 32 minerals for like a $15. We're gonna take that opportunity. I don't know the details, but they will do a full analysis on that sample.
Sounds great, because if this plant protein becomes ready and the phosphorus and potassium content is not that high, it's a good option even in kidney disease, because it is plant protein, the amino acid profile is different. Just the concern is about phosphorus and potassium.
Totally agree with you, and been in conversation with one of my master students in my class, Steve, hiding somewhere. Steve? Oh, he's no more here with us. Anyway, we talked about the minerals and how we find a way to analyze all these minerals, because we always focus on sodium, but
yes,
we ignore all the other traces, which is so important.
Yeah.
Important to maintain a level that keep you healthy, improve your hormone, immune system depends on it. But at the same time, you don't want to get a toxicity from those minerals. But nobody actually looking at these, because they are not required in the nutritional label by FDA. So nobody really go in depth unless it's sodium. That's the only thing I need to declare.
Then it's so good that you will check it. And even in liver disease, because it could be toxic if the amounts are higher, or even better for them. Okay, sounds great, amazing. Thank you.
Great question.
Hi there. I noticed at the end of the slides there, you had stats for control and you had stats here. So you have the control and you have the fermented. Did you extrude the fermented and the control, or is the fermented non-extruded? I'm a little confused.
I'm so glad. That's a great question. Where is Ali? Okay. So Ali did most of the analysis with Shirley. And what we did ferment and extrude. But here I eliminated, in the previous slide, I showed the extruded, the fermented. So we have the control, the fermented, then the extruded, because we wanted to check the extrusion effects on the flavor. And we're doing the same thing for the functional properties, for minerals, because as Yobing mentioned this morning, there's not much study on how much damage can cause by the process. And go to the question of Mr. Shah, the frying, because this is way higher temperature than frying. So we are studying this changes. I think Jing is working on the processing of the data. And on our side, we're working on the nutritional value. We're working on the PDCAS. We're working on the functional properties. So yes, it's control, fermented, extruded, because we wanted to see the impact of extrusion. Because maybe we say, oh, extrusion is so bad, just consume the powder, which will not work. But maybe use baking or other techniques.
So both of the numbers in those columns have been extruded as well?
Those are just the control and
Okay.
fermented. So the
Sorry.
extruded
Thank you,
is
thank
actually
you.
here. Yes, as you see, the second one is extruded.
Perfect.
That's fermented extruded. Should
Thank
be
you.
corrected. Yes, thank you.
Yeah. So the great presentation. The question is: does your fermented process result in a finished product where the fermentation can be produced and a fermented ingredient supplied to the final production industry? So is it shelf stable after it's fermented, or does the fermentation have to be in the final manufacturing process, is the question.
Great question. That's why we're doing the downstreaming, because in my simple process now, I'm not going for commercial. We did dry the powders. So we made sure the water activity dropped to below 0.6 and the water contains 7%. So it's a shelf stable at room temperature for at least 12 months.
After fermentation?
After fermentation, but
Okay.
with the drying. That's why I put there the
Okay.
downstreaming is the drying techniques. We want to dry it, but we don't add up too much to the cost of the process.
Great. Knowing that, then I'm going to come back to we need to do a better job at propaganda line, and that is when you call it, the title of your presentation, a scientific article, bioprocessing, right there, you've just turned off all the consumers who think anything artificial, bioscience, they have associations with, they have all kinds of negative associations they've been trained to have for that bioprocessing label. Fermented, on the other hand, has all kinds of positive associations. People are trying to eat more kimchi, prebiotics. They know that fermented is good. And so fermented is a great label. Bioprocessing is a terrible one. And superfoods is a great label, but when you call it super pea powder, that's sounding like yet another artificial, factory-produced synthetic ingredient. Why not just call it fermented peas? Because you've changed the pea powder by fermenting it. If you call it fermented peas, that sounds natural, it sounds healthy, and if this is an ingredient that you can give the label to, that your downstream producers can put on their ingredients fermented peas instead of pea protein isolate, then you've started to change the public perception of this is actually a really healthy ingredient. You've done the science to prove that it's healthier, to prove that it's more stable. So the suggestion is, if it's shelf stable, use fermented, not bioprocessed, and call it a superfood. It's in the superfood category, but when it's on the ingredient label, if you can get fermented peas as an ingredient that's authorized on labeling, you've just solved the protein pea isolate negative associations as well.
Great question. I would like to ask the students and Professor Marcus Salam, please come here front. There's a lot of space. Please, students, join us here in the front. And it's a great question.
A great product.
Thank you. I'm so privileged to work in an institute, have 8 colleges, and in a college that have 5 different departments. Because as I mentioned, working with agribusiness, my colleague Julie and Denise, please stand up, Julie and Denise. It was really a privilege because I learned something about consumers. So when we want to get funding and we want to sound like a startup and talking to people in the Bay Area, we say bioprocess. When we go to Pomona, we say, oh, fermented and healthy. So she is helping us to navigate and explain things to people based on the level of understanding and the perception. It's nothing different. It's exactly the same superfood. However, it's the way you present it will make a difference. So we use the bioprocessing in some of the big terms and whatsoever, but we actually, as I mentioned, is a fermentation, is a simple, is nothing new. We've been producing tempeh for the last 2,000 years. It's exactly the same process.
We have time for one more if anybody wants to put them on the spot.
Tired, Kalina. I have another discussion.
Hi, I don't know, I might have missed it, but I wanted to find out how much wastewater do you actually have from this process?
That's a good question. I don't consider it a wastewater because we dry it, so it's going to be vaporized, and everything in the product will stay. So we don't generate waste from the water. We dry it. And since we have about 40% to drop it to about 10, 12%, it's less energy, and usually we will not generate any water. Compared to liquid state, you have a lot of water, 90, 95%. So far for small process, we didn't get any water waste. It's usually all evaporated. And that's why we're looking at the downstreaming. We want to find a technology like a tower drying or something, a continuous process, affordable cost, and no waste generation.
Thank you. All right. Well, thank you so much, Dr. Hasan. Appreciate your presentation.